things before we jump in and do the physics, okay? First of all, hello, I didn't even know it was coming, but apparently it is. Parent-teacher conferences are tomorrow. What? I know, that's what I said. It's like, oh, okay, it was been on my calendar since the beginning of the year, but I was like, hello. All right, so in case you also needed a reminder, tomorrow evening from 4:15 to 7:45 in the main commons, I'll be there. I'll bring candy. It'll be a great time. Invite your parents. Come along with them. We can talk physics. It'll be great. So I just want to make sure you heard that and you know that. I want to tell you a couple of things about logistics for the week. I have not yet updated the Canvas calendar. So if you looked at that, I apologize if it was confusing to you, mostly because we were supposed to have a check-in today. Take those out, please. Hey, Lewis, take those out, please. Thank you. Okay. We were supposed to have a check-in today, but we don't have a check-in today because we didn't have school on Friday. So just a heads up about what is going on this week. Tuesday and Wednesday are a focus on Newton's third law, Newton's third and most important law. We're going to establish it. We're going to write it down today. We're going to spend some more time with it tomorrow. At the end of period tomorrow, we will have our 4.3 check-in. Okay. So I'm going to give you some homework to do tonight. It's a little half sheet with just a couple of problems on it. I would strongly encourage you to spend a little time working on that today so that you are ready to go. Because again, we're checking in on Wednesday. Why? Because we're at the end of the unit. We're going to review on Thursday, and we have our Unit 4 test on Friday. Okay? I have not put Unit 4 content into the into PowerSchool yet because I'm waiting to get that test in, and then all of that will go in as well. So right now, your PowerSchool grades are only based on the Unit 3 stuff. Okay? Questions that you have about the logistics of all of this coming up? Okay. What we have done is not like mind-blowing, but there is a lot of stuff there. So I want you to be aware of that. You will need to spend some quality physics time this week. Okay? You good? Okay. I just want to, if you have questions, let me know. Okay. Before we jump in to do our actual physics today, I wanted to give a shout out to Mr. Beringer, who is our new student teacher. So, yeah, right? We're excited. They will clap every day for you if you want. So,
Beringer?
Yeah.
Mr. B.
Sorry. No, you're okay. So Mrs. Gribble is now doing her student teaching at Linmar, and he came from West. You were at West doing practicum last semester for you, and will be here with us for quite a few weeks, right? How long are you here? Awesome. So until May 8th. So for a long. So yeah. So he'll be up. Exactly. I'm going to ask that you give him your attention right now. He's going to introduce himself. And I'm going to remind you right now that you do not need your cell phones out at all today, so put them away. Okay? I know you've been sitting with your cell phones for 4 days and staring at them. Today is a day of cleanse, okay? Get rid of it. Take it away, my friend.
I'm going to be certified to do chemistry as well, but I like this more. I grew up in Western Iowa on an acreage. I lived in Oklahoma for about a year or two. Lived in Iowa City for the past 10 years. I'm pretty old. I'm not a standard college student, so I'm about 26. I live in Iowa City with my wife and our 2 rabbits.
That's awesome.
He said he's going to bring us a picture of his rabbits soon. I'm excited. What are your rabbits named? What are your rabbits' names?
One boy is Oliver and the girl's Evie.
Cool. All right. There you go. All right. So just want to remind you that we're welcoming him into our community. He'll be here every day, right? He'll be here all the time with us. So that's awesome. All right. We are going to jump in and get started with some physics. Friends, I'm going to let you know that what I'm asking you to do today is to turn your brains on, not only from the 4-day weekend, but also getting things back at the front of your physics brain from last year, okay? From before winter break. Because Standard 4.1, which we are assessing on Friday, happened in December, okay? You will need a calculator out. You will need a pencil out. You will need a paper or your warm-up sheet out. And your equation sheet would also be helpful, okay? I'm going to give you a few minutes to get started. If you're not sure where to get started, where's the best place to start? Write down you got it. Get started, friends. All right, my friends. First of all, do you understand what's going on in this problem? How many kids are involved? 2. What's Carla doing at the beginning? She's just standing on the ice, right? She's wearing skates or maybe not. I don't know, but she's standing on the ice. And then what happens? She starts to move. Why? Because Donna pushes her. Yeah. And what happens to Carla after Donna pushes her? It doesn't say she falls. It just says that she's moving. Well, Donna might. We don't know much about Donna, do we? But we know enough. So let's go ahead and just start with our givens. Because when you're not sure what to do, givens are a great place to start. So help me out. Let's make a list. What have you got? 27 kilograms is the mass. Everybody good with that one? All right. I need more givens. What else you got? Yeah. You got it. Initial velocity for Carla is 0 meters per second. Thank you. Thanks for the explanation. So I appreciate that. All right. That's 2 givens. There are a lot of things that we know in this problem. Add what else you got? Okay. So 0.2 seconds. And that's equal to time. Yeah, the time for the force being applied. You're exactly right, but I'm just going to write it as time for now. That's perfect. All right, we know more things. What other things do we know? You look like you had your hand up there, no? Awesome. The final velocity for Carla is 1.9 meters per second. Oops, that's really kind of ugly. Sorry about that. All right. Are there any other givens that we know? Any other things that we know for sure? Sometimes problems are intimidating. Will you need to know a problem like this on Friday? No, so let's make sure that we know how to do it, right? If you get stuck, you look up at the plan, right? We wrote down our givens. The next thing we need to write down is our unknown. What is the thing in part A that we're asking for? What are we trying to find? This is way more fun when I have to call on you. Raise your hand if you can tell me if you can read the question. I'm going to call on different people, though, so it's not just Adsto. I want everybody to help me out. Was that the force, right? With what force did Donna push Carla? So really we're asking the force of Donna on Carla. Okay. So we've got our givens. We've got our unknown. We're making progress. Now we need to find an equation. This is the time. Now we need to find an equation. If you do not have an equation sheet out, go ahead and pull it out. If you don't have yours for whatever reason and you want to borrow one of mine, let me know. I can bring it to you, or you can come up and get one. I want you to look and discuss really quickly with your partners what equation makes the most sense. Does anybody else need an equation sheet? You else need one? Remember I said this is from right before winter break. You're looking in that second box, the dynamics box. Do we care about acceleration, you guys?
Shut up.
Dynamics section. Dynamics section. Look at the dynamics box. Look at the bottom of the dynamics box.
Bottom?
Yeah.
All the way?
All the way at the bottom of the dynamics box. What do you see there? So what did you say? You said impulse. And what is impulse? Okay. Delta P equals F delta T or just T. Did y'all see this equation? Now, Ben, I could ask you, why did you choose this equation? And that's what I thought you were going to say. But let's work backwards. Tell me why. Yeah.
Because we have delta P.
Okay. Do we have?
We don't have delta P. That's what we're looking for, right?
Well, the unknown is F.
Okay. Well, we don't have delta P then.
But so that's what I was about to ask. Do we?
Yes.
What is P?
We can do F equals F. No.
You could. That'd be a lot of work. Oh, there we go. Okay, say that one more time. That's a lot of work, buddy. All right. So I'm going to go with what Grace said.
Where'd you find that?
Well, and so Ben, I do want to answer this question for you. And friends, I really want to make sure you're listening. I know that you've been kind of not in school mode for 4 days, but I really need you to focus back here because we only have 4 days now until the test. Right? 4 days from today is a test where a question like this may show up, and you want to make sure you understand it. Tuesday, Wednesday, Thursday, Friday. Yeah, it's Tuesday. Okay. So Ben says, how am I going to find that out? Grace said she found it in her notes, but she doesn't get to use her notes on the test.
No, it's on the equation.
But it is, isn't it? P is equal to mv. Delta P is equal to m delta V. You gotta use a little physics knowledge to do that. What does delta mean? Change in. So we could write that one more step, can't we? We could write that as m times v final minus v initial equals f times t. Yeah? I'm gonna give you a minute. Plug it in. Find an answer. Go, go, go. Everybody's doing it. Move that pencil. Make some graphite. Make some graphite marks. You do it. Don't wait for somebody. I'm assuming I walked in on a conversation I shouldn't have been hearing there. Using inches. What is this? All right. So friends, let's make sure we got this. Do you feel like you had an answer? What were you solving for in this equation? F, how do you get F all by itself? Divide by T. Thank you. So those T's are going to go away, and you can solve for F. And what do you get for the force? 256.5. 256.5 what? Newtons. Okay, that's kind of a big force. Kind of a big force. Kind of a big force, but it's only for a very short time, which is what caused that change in velocity, change in momentum to be so big. Hey, just real quick, you said it, but I want to write it down, and you might want to write it down in your notes as well. This equation right here is called the what? Where does that come from? Starts with an I. Impulse momentum theorem. Just trying to remind you. So that was part A. Let's take a look at part B. Do you have an answer for part B or a way to solve part B? Didn't you just what? We just solved part A. No, talk to me. I think you're actually right. I was just being goofy. No. You are correct. In fact, that is true. Can you say that a little louder and with more authority because you're exactly right? So you can multiply F times T to get the change in momentum, right? Any other way to do that? What if I screwed up and this was actually something else? You could do the mass times change of velocity, right? Same. So for part B is really just solving this part of the equation. Mass times change in velocity. What did you get for a value for the change in momentum? Did you get a value? If you haven't yet, you have a calculator just so eager and ready to tell you the answer. All you need to do is do some multiplication. So do it real quick. Do it real quick. Figure out that change in momentum. So make sure you do it. Check with their table mates to make sure they got it too. Don't overthink it, friends.
That's what I got.
Dawson, did you get it? Oh, do it quick because we gotta go. So much time. But I like to call on you.
So where'd you get?
Where'd I get what?
No, you just used the impulse momentum theory.
I did. I'm just gonna use the change of momentum part because it's easier. So it's just mass times change of velocity. Do I call on him every day? I don't know. I love you guys. Oh, it is. I'm sorry. It's just 'cause I like you guys a lot. What'd you get? 51.3. Do you guys agree with him? Awesome. What are the units for this thing?
Kilograms, meters per second.
We can figure it out, right? M is in kilograms. Velocity is in meters per second. Change of momentum is in kilogram meters per second. We good? All right. Part B is done. Now, part C is the big part. If you have not been paying attention until now is your time. If you haven't paid attention, then stay with me. Okay? But if you haven't, this is it. Right here. Part C. Did Donna experience an impulse? Andre says yes. Raise your hand if you agree. You think yes. He experienced an impulse, or she experienced an impulse. Raise your hand if you think no. Why would she have experienced an impulse? Tell me if you haven't raised your hand yet. You say, I really don't know, but I'm eager to find out, Miss Carbling. That's okay too. That's why we're here. If you knew all the answers to all the questions, why are you here, right? So here we go. Let's ask. We don't have to be in this class though. Put your phone away, dude. Like seriously. I don't even think that's true. Right. Like it just doesn't work. So you can put it up here and then it won't be so tempting. All right. Question for you. If an object or person is to experience an impulse, what does that mean? Say that. They experience a change in momentum, right? So question is, does Donna experience a change in momentum? What evidence do you have that she would have to experience a change in momentum? Whoa, it just came out like you didn't even know it was there. What did you say? Conservation of what's the one we've been conserving lately, friends? Momentum. What? What does conservation of momentum mean? No. They mean different things. All right. I mentioned that this is the kind of problem that you might see on Friday, which means I need you to be with me here, friends. So it came out of her mouth without even realizing that it was there, but that's exactly the right answer. It is because of conservation of momentum that we know that this is true. And Grace added in there, what did you say? You know this, whether you remember it from last week or not. We spent a lot of time showing this. We did it qualitatively, we did it quantitatively, we did it a bunch of times to figure out if these things were true. We also said that we could say that the change in momentum for one is the same as the change in momentum for another. Does Carla experience a change in momentum, you guys? Look up here. Does Carla experience a change in momentum? How big was it? How big? 51.3 kilogram meters per second, right? If Carla experiences a change in momentum of 51.3 kilogram meters per second, how big of a change in momentum does Donna experience? Not even hypothetically, like in for real life. Doesn't matter. And it's weird, right? But we did this. We showed this a bunch of times. Just remember we did last week where we had all those different collision situations, right? You had a pink sheet or a yellow sheet or a green sheet or a blue sheet or whatever. And in all of those cases, you guys, in all of those cases, you were trying to prove that the change in momentum at the beginning, or change in momentum for one cart, was the same as the change for the other cart. It didn't matter if one cart was coming and hitting the other one and moving. It didn't matter if they were standing still and pushing off. It doesn't matter. Momentum is conserved all the time, as long as there's no outside force. So, does Donna experience an impulse? What's the answer? Yes, she does. How big is the impulse? Negative 51.3 kilogram meter per second. Okay. That was a long warm-up problem. Taylor was surprised when she walked in. We were still doing a warm-up problem. It's kind of crazy. Why is this such a good warm-up problem, though? It's got everything in it. It is all there. We're going to put it into some words right now. On Thursday, if you were here, you got this really nice bright pink sheet of paper. If you were not here on Thursday, raise your hand and we'll get you another one. We just need to know and then we'll get it for you. Anybody else need the bright pink piece of paper? Did we write anything on the front of this piece of paper or no? Just on the back. Okay, that's cool. Got you. I just couldn't remember when the bell rang. All right, we're gonna do the front right now. Who knows?
We have 18 minutes.
18 minutes. I only need 15 minutes. Anybody else need one? All right. We get out at 18. And it is 11:01, so now I have 17 minutes. So that means I need to move quickly. Here we go, friends. We are going to do all of Unit 4 in 17 minutes. You go to the bathroom. It's okay. All right, here we go. Standard 4.1. We got to stay focused. Standard 4.1 was the impulse momentum theorem. Standard 4.1 focused on one object. Okay? And it was the result of a force acting on the object. Pretty straightforward. So this is Carla and Donna right here. All we were talking about was Carla and the result of the force of Donna on Carla, right? We know that as a result of the force of Donna, Carla had a change in momentum. And that change in momentum was equal to the force that Donna applied times the time with which she applied it, right? Same thing that we talked about with the eggs before winter break, right? And when we were throwing eggs, when we were dropping eggs, in all of those cases, the change in momentum was equal to the force times the time. I'm going fast, I know I am, but we gotta keep cruising. So I'm gonna go down to the conclusion section. I'm just gonna go over here. Is that okay? No? Okay. You guys have to stay focused with me. I told Ben I was gonna get this done in 15 minutes. I can't do it if you can't move fast too. Okay? He's just trying to prove me wrong. That's what it is. All right, here we go. The conclusion. Impulse momentum theorem conclusion is that a force acting on an object over time results in an impulse. That's a key word. Okay. Which results in a change. Oops, hold on. in the object's momentum. A force acting over a time results in an impulse, which results in a change in the object's momentum. That was the Unit 4 stuff that we did right before winter break. Okay. But again, we're assessing that on Friday, which is why we're spending time going over it now. Okay. I'm going to keep cruising. This is all going to be up on Canvas, so you can take a look at it there as well. I'm going to go back to number 2. Here we go. Number 2. 4.2 is what Sierra had said before. It is the law of conservation of momentum. Unlike the impulse momentum theorem, the law of conservation of momentum focuses on 2 objects. It is indeed an interaction between 2 objects. Okay? And those 2 objects are in a closed system. We've mentioned this term before, but I want to make sure that you know it and that you've got it. A closed system is one in which there are no outside forces. So again, the distinction here, impulse momentum theorem is one object. Law of conservation of momentum is 2 objects. It's an interaction between those objects. Okay? There are 2 different ways that we can write the law of conservation of momentum. And in a perfect world, if I had an extra couple minutes, I would go through the derivation between them. But friends, we've already done it. Okay? You have it on old notes. You have it on old recordings. So I'm just going to give you the 2 kind of ways to write it down. Okay? Approach number 1, thank you for the update, is the initial versus final. This is the one that we said just a minute ago, okay? And that is that the total momentum at the beginning within a system of more than one object, okay? Or actually any objects, is equal to the total momentum after. I'm going to write that out one more way just to make it really clear. So it's the momentum of A at the beginning plus the momentum of B at the beginning. And that's the same as the momentum of A at the end plus the momentum of B at the end. Yeah. Like this? Total. I'm sorry. Yeah, I'm writing fast because it keeps telling me how much time I have left in this stretch. That's all. Just thank you for asking. Please let me know if you can't read something. I'm always happy to help you. Okay. The other approach was the original approach that we used, and that was to look at the 2 objects separately. And in that statement, it's the same law, you guys. It's just a little algebra. We can also say that the change in momentum for A, actually the opposite of the change in momentum for A, is equal to the change in momentum for B. Okay? So these 2 things here are both statements of conservation of momentum. Okay? They're both statements of conservation of momentum. I'm going to go ahead and write down a conclusion. Is that okay with everybody? All right, we're going to move down just a little bit. We're going to say, just in words, that the change in momentum for one object is equal to the change in momentum. Oh, I should say equal to the opposite. of the change in momentum for the other object. So this is just writing out in words what that means. I know that for some of you, the equation makes a whole bunch of sense. For some people, the equation just looks scary. So these are the words that go with that. So the 2 weeks before winter break, we spent on standard 4.1. That's the impulse momentum theorem. The first 2 weeks after winter break, we spent on conservation of momentum. And now we're going to spend 2 days on number 3. Why? Because it's just putting the other two together. Okay? I'm going to scroll back up. Got just a couple minutes, which is just enough time to do 4.3. Perfect. 4.3, as I said, is just a combination of the impulse momentum theorem, which is 4.1, and conservation of momentum, which is 4.2. But it has a fancy pants name because Isaac Newton thought he was the coolest and had to name everything after himself, right? So 4.3 is actually Newton's. I don't really like Isaac Newton. I'll tell you another day because I only have 6 minutes left. It's not because I'm jealous, I promise. All right, here it comes. This is it. This is the stuff we got to know right here. All right. I'm going to start with standard 4.2. Conservation of momentum is say negative delta PA equals delta PB. The change in momentum for one object is opposite the change in momentum for the other. And then I'm just going to zoom out for a minute and say, hey, but wait, the change in momentum is just force times time. So anywhere I see a delta P or delta P, I can write an F times T. That's all I'm doing here, friends. So I'm going to do opposite of the force on A times time is equal to the force on B times time. No big deal. Now, the force on A, who pushed A? Say it out loud, Annie. B. And who pushed B? A. So instead of just writing on A and on B, I can write the force of B on A and the force of A on B. Who pushes first? Any idea? No. A force is just an interaction between two objects. It's just contact. The force starts when they touch, and the force ends when they stop touching. Who touches first? Does that make any sense? It doesn't make any sense. In fact, the time is exactly the same. The time for the forces is exactly the same. Allison Boris, right? This time is exactly the same. So those times are going to go away. And this right here is the thing you're going to put in a big box with your glitter pens and all that. The force of B on A, the opposite of that is equal to the force of A on B. This is it right here, friends. This is it right here. Okay? That is Newton's third and most important law. It's a big deal. It is a big deal. I'm going to write it out in some words. Oh my gosh, see? Jeez, you guys are so demanding. I know, and I don't have time. Gotta go. It's okay. I can handle it. I've got a bunch of minutes still. No big deal. I know. 2 minutes. This is it right here. Just hold on. So don't put your stuff away, you guys. You're not done. If you're going to give me a time limit, then you have to give me the time. I need you to be quiet. Let's write it down. When two objects interact, each exerts a force on the other. Okay. The forces are the same size and they're in opposite directions. So Kaylee just asked what the quiz is going to be or the check-in is going to be over. So let me explain this. There is a lot that goes into that statement, okay? I'm giving you a few problems to work on tonight. Do not ignore these. If you're going to be ready for your check-in tomorrow, you have got to work on these tonight so we got something to talk about tomorrow, okay? Take one and pass it back. Make sure that you get there, okay? And then, hold on. Don't put your stuff away because I need you to turn that sheet around, that pink sheet. Turn that pink sheet around. On Thursday when we were here, we started this whole conversation with a couple of people. Do you remember who they were? Alice and Boris. And do you remember that day I asked you 3 questions? And right now, before we go, because we still have time, I made it with plenty of time, so you've got 3 whole minutes to answer these 3 whole questions. Here they are. Remember, Alice and Boris were standing on the ice. The questions are, who pushes first? Who pushes harder? Or longer, and who pushes harder? I want you to write down answers on the back of the bright pink sheet right now to those questions. Talk to your table. Don't turn your brain off yet, you guys. You got to do this. Right? That's why I'm asking the question. So answer the question that's being asked. Yeah. They are not. We're going to talk about it tomorrow. Yeah. I will, because I don't want to. I'll think about it. But you should be able to answer them. Remember the 3rd law, and you should be able to answer all of them. Did you answer them? Let's talk in a minute, shall we? Yes, please. Who pushes first, you guys? What'd you decide? Same. They both start at the same time, right? The reason that you care about this, how many of you have siblings? How many of you occasionally fight with your siblings? How many of you have siblings that pick on you? Right? Or maybe you pick on them. If you go and tell your mom or your sibling says, but she pushed me first, what's the right answer? Who pushes first? Nobody pushes first. You don't have any, they can't blame you now. Right? It's good. Who pushes longer? Who is picking on who longer? No one. And who pushes harder? No, that's, okay, guys, shh, sit. Shh. The bell has not rung and it's still my time. I will hold you after class if you can't be quiet. This is the whole point. You didn't get it. I need you to get it. Who pushes harder? Your big brother or you? It's the same force. Why do you fly across the room while your brother just sits there? He's got more what? Mass. So even though the forces are the same, what's going to happen to you because you have less mass? Use physics, friends. What's going to happen to you? You are going to accelerate more. Okay? I'll see you tomorrow.
Easy on, right?